Hello everyone. Welcome to the problem solving session for the data structures and algorithm design course. So, yeah, I think you might have already watched the lectures corresponding to the week one content. So, some of the prerequisites for this course would be some familiarity with basic algorithms, like such as basic sorting algorithms and so on, and some familiarity with the notion of asymptotics. Although uh, we might introduce define these notions quickly, but it would be easier to grasp if you have some familiarity with some basic algorithms course. This is a slightly advanced course that builds on top of the basic ideas. And so in this uh, in this live solving sessions, we will take up some problems and try to solve them. Some of them uh, we may not fully solve, but you can take it as homework. And so this is a 12-week course. We will have 12 sessions of 2 hours each, and the slots are fixed. Tuesdays 7 p.m. to 9 p.m. Okay, and there will be this one extra week. Yeah. S- okay. And there will be this one extra week where we'll discuss the slot towards the end. Um, and these sessions are recorded. So you'll find this link on the Swayam portal. So all these sessions will be uploaded on YouTube, and the notes, whatever we discuss during the sessions, that will also be uploaded. Okay, so I'll tell you, yeah, I'll just introduce myself. So I'm Neha, and I'm a PhD scholar at IIT Madras, and my area of research is algorithms and complexity, mostly complexity. Okay, so okay, so are there any questions about? I mean, any general questions before we start solving? Uh, okay. Okay. Yeah. So consider the following problem. You have an array. Okay, so you have an array A of, let's say, n elements, and it is not necessarily sorted. So the elements are in arbitrary order. Okay, and so normally if you apply your sorting algorithms, what's the best running time you can do? Um, if you want to, if you have answered, please unmute and let us know, or you can even use the chat box. I hope the question is clear. Um,
क्या कर रहे हैं
okay,
थोड़ा
so
it's not possible.
okay, so what is the running time, the worst case running time for the algorithms that you are suggesting?
And factorial one
N factorial. So can you do better? Um,
and square
N squared, even better if you use, let's say, merge sort.
and
Uh,
log n
Good, yeah. N log n. Can you do better than n log n?
Problem solving
Constant one. One.
for that, ma'am, we can use the constant, which has an time. I think 10 seconds, something like this. I'm not sure, but
Okay,
basically.
okay. So this okay, so merge sort gives you n log n, and in fact it can be shown that you cannot do better than n log n. So any comparison based sorting algorithm must in the worst case requires n log n operation. So there's a nice proof for this, but we will not get into it. So in fact this is in fact optimal. So any comparison based sorting algorithm requires omega n log n comparisons. Okay, so this is the case when a is an arbitrary array. There need not be any relation among the elements. Okay, so now consider the following. Okay, yeah, so let me just ask one more question since I see some comments. So if you use insertion sort, for example, what would be the running time, worst case running time?
O
N
of
square.
n square.
Correct. Good. And same is the case for selection sort and so on. Okay. So it seems that merge sort might be a better option because this is asymptotically better. Okay. So uh, yeah. So now consider a slight modification. Okay. Instead of giving you an arbitrary array, we are giving you some guarantee. So what is the guarantee? That every element in this array is at most 10 places away from its correct position. So if you look at this element, for example, it should lie somewhere here. Okay, like within the 10 boxes. Okay, that is true for all the elements. So given this extra information, uh, merge sort will still give you n log n time, because what you're going to do is you will divide and uh, keep on divide and conquer thing. Okay, it will still give you n log n, but if you use some other algorithm, can you do better than n log n given that you have this extra promise?
We can use a combination of merge sort and insertion sort, that it can do the sorting in a way that uses the merge sort after insertion sort is done, so we can get optimal time.
We can also use the uh, which one is
Yeah, sorry, Nikhil, can you repeat what you said?
ma'am. Actually, there is algorithm by binary something
Binary search or something?
sorting.
uh, okay.
Binary setting maybe, wherein actually it based on the divide and conquer basically.
Okay.
If I,
Okay. So okay. So okay, are there any other answers if before we discuss the solution? Okay, so if you use insertion sort directly, uh, yeah, if let's see what happens if you use insertion sort directly and just analyze. Okay, there's no change in the algorithm, just analyze what happens. Okay, so okay, so let's look at the contents of a1. Okay, so this element is already sorted. I'm just arbitrarily writing some values. Okay, and now you look at the second element, and we are trying to place this element in its correct position. Okay, so let's say this is 12. This is also already sorted. So let's say We are talking at the ith instance. You keep on repeating at ith position. You have a sorted array here. So this is your sorted array, and you're trying to insert the I plus 1th element. Uh, sorry, the I plus 1th element, which is, let's say, 42. Okay, so what is the time taken to place this 42 in its correct position? So let's answer that. To put position, given that uh, the the array before it is completely sorted, given that, I'll denote this by a of 1 to I is sorted. So how much time does this take?
How many elements are there in the array?
Okay, so you have I elements that are already sorted, and you are trying to put this I plus 1th element in this array of size I plus 1.
Ma'am, if we consider placing the one element in one array, then it time requires I plus 1 seconds, ma'am.
Correct. So it
I think
requires I plus 1
I plus one
instructions.
element.
But
Uh,
now, uh, but now observe that you are given this additional promise that if you look at any element in the array, it is at most 10 positions away from its correct position. So if you look at this element, it cannot be all the way here. Okay, the maximum, like the leftmost position that it can be is 10 steps back from where you are. So maybe this is mm, okay. So does this make sense?
yes, ma'am.
Okay, so you only need to go 10 positions. You only need to go 10 positions before the current element. Yeah, is there a question, Geeta? Okay, so sorry, just a minute. Okay, so yeah, so is this clear that you don't really need to go all the way I plus 1 steps all the way? You only need to go 10 steps. Sorry, I don't mean instructions, I meant comparisons. Okay, so you only need 10 steps of comparisons per element. So what is the algorithm now? You look at a new element, go at most 10 places back, put it in its correct position, and then go and look for the next element. That's your outer loop. So how much time does this take overall, the sorting, I mean, this sorting algorithm?
Log 10 to the base 2, which gives approximately 4 steps.
Why is it logged? Like in the worst case, you will have to go 10 steps back, right?
Ma'am, could you please repeat the question?
Yeah, so we are saying for putting one element in its correct position, you need at most 10 comparisons. So overall, to sort this entire array of n elements, what is the total time?
Ma'am, we need to sum each and every element placing, ma'am. For example, the element is 8, right? So it requires 1 second. If the element is 2, it requires 2. 2 plus 1, 3. So similarly, we want to sum every element insertion.
Yeah, you want to sum that for every element, but for every element you have a guarantee that at most 10 steps, at most 10 comparisons are to be done.
Okay, then we can multiply by 10, ma'am.
Yeah, exactly. So for every element you need 10 steps, so altogether the time is 10 n, which is order n. Okay, as some of you have answered. Also, yeah, there's one comment here which says that index starts from 0, not 1. So I'm not constraining myself to any programming language for now. Okay, so if you're talking about C program, yes, your array index starts with 0, but we are just talking theoretically for now. Um, okay, so I'm using the freedom to start my array index with 1. Okay, so okay, so is this clear? Um, are there any questions about uh, the algorithm and its analysis? Okay, so yeah, so you can do a similar analysis for the other algorithms as well, but uh, you will not find a significant improvement because insertion sort uses in its I mean, philosophically uses the fact that you are only looking within the locality. Like, okay, so you'll end up using insertion sort in this case, which gives you a good speed up. So instead of n square or n log n, you're getting a linear time. Okay, so the takeaway from this question is that in general, your algorithm could be doing worse, but if your data admit certain properties, then you can utilize those properties and I mean get better algorithms, or the analysis itself can give you a better time, which is the case here because we did not change anything about the algorithm itself. The algorithm runs as it is, but the analysis gives you a better time. Yeah, yeah, Goel. So that observation is correct. If you use mud sort or quick sort, this additional property that your correct position is within 10 may not help you because merge sort and quick sort will divide the arrays and do arbitrary comparisons with it. So this property may not be useful in that algorithm. Okay, so any other questions or observations? Okay, okay. So let me define something called inversions. Some of you might have seen this. If you have seen merge sort, then you know what inversions are. But let's say let's say A is an array, and you look at pair. Okay, so let me just take an example. So let's say this is 5, 6, 4, 2. Okay. Okay, so let's say this is my array. This is not sorted right now. Okay, elements are in, let's say, in this order. So if you look at the element a1 and a2, uh, which is smaller, a1 is smaller than a2, and if you look at the index 1 is smaller than index 2. Okay, but if you look at elements at the second and third positions, okay, so 2 is less than 3, but what about the values? If you look at the values at the second and the third position, it's not respecting the order, right? So if this is 6 and this is 4, so you sort of see an inversion. The positions are in a different order, but the values at those positions are inverted. Okay, so this is called an inversion. So this pair 2 comma 3 is an inversion. Okay, so if you, what is the total number of inversions in an array? You look at all I comma j pairs. This is the number of I comma j pairs where I j are in n, I is not equal to j, and the values don't respect the order of indexes. Okay, so is the definition clear? Okay, so let's, okay, yeah, some of you have already answered what the total number of inversions in this, okay, in this array. So let's find out. I'll call this 1 2 3 4 5. So 2 3 is an inversion, 2 4 is an inversion, 2 5 is not an inversion. Then mm, yeah, then you look at 4, sorry, okay, sorry, let me do this again. Okay, so 1 2 is not an inversion, 3 1 1 3 is an inversion, mm, 2 3 is an inversion, mm, okay,
2 4, ma'am.
yeah, 2 4 is an inversion. Then 3 4 is an inversion, and 1 4 is an inversion.
Yes.
Okay, so there are 5 inversions here. So let's say your array is sorted. Then how many inversions can be there? So let's say A is a sorted array on n elements. What is the total number of inversions? Yeah. Yeah, good. So yeah, all of you are right. So there are no inversions. So the number of inversions, in some sense, is a measure of how sorted your array is. If your array is very close to being sorted, like there are only few elements that are out of place, then you will find fewer inversions and so on. Okay, so that's, yeah, that's the idea. So now, in the previous question you saw there was an additional property which made your algorithm work better than n square or n log n. So here you have some other property. You have a property that your array is guaranteed to have k inversions. Assume that k is some constants. There are at most k many inversions. um, so instead of going with the n log n worst case algorithm, can you do something better to improve this time? Okay, so a couple of you are saying it should be k log n. So can you explain what's the algorithm and analysis? Yes, Manas.
Hello, am I audible
Yes, yes,
properly?
yes.
All right, so I use the elimination method, and if we consider that there are no inversions, then it would then the D option would tend to infinity. And if there are no inversions, then we would give us zero as well, which would uh, which would be lesser. So that's how I thought of it. And if we are using k inversions, then it is supposed to be better than n log n. That's why.
Uh, so if so, I mean, why can't it be, let's say, k square log n or something? I mean, it, even if it's better than n log n, it could still be worse than k log n. Um,
I answer based on the current option. That's why.
okay, okay. And those of you who think it's option C, do you want to, um, I mean, share your thoughts? Did they?
Ma'am, I feel like the answer should be C because it's pretty straightforward. I mean, if you consider n elements, so the outer loop is for, if we consider n minus 1, it goes from 0 to n minus 1, and the total elements are n. So, considering that as the outer loop and having total number of inversions as k inside, both these cases should be added to get theta of n plus k. So it's pretty straightforward, I think.
Okay, okay. Yeah. So yeah. So I see one comment which says you take theta of n time to scan through the array and theta of k time to perform shifts to fix the inversions, which is yeah, I think similar to what you said. So indeed, that's the correct idea. But in this course, we will formalize the intuition. So that's the idea throughout the course. So whenever you have a reasoning, you will mathematically uh, prove that indeed this n plus k should be the correct answer and nothing smaller than that. So I'll just uh, write down whatever, yeah, your thoughts were. So um, okay, so you are kind of using the insertion sort here. You are assuming that some some part of your array is, let's say, already sorted, and I'm looking at the I plus 1th element, and I want to put this in its correct position. So observe that, let's say, this element I plus 1. Okay, I'll just admit a few more people. Okay, so let's say a of I plus, let's look at the a of I plus 1th element and look at the number of inversions that it has with any of the previous elements. Okay, so look at this array here and see how many violations it makes with the previous element. So essentially we are looking at j comma I plus 1, where j is between 1 and I, but a of j is larger than a of I plus 1. So we are looking at all such pairs. Okay, and let's say that this value is some L. So this is the total number of pairs with which it has violations. So where can its correct position be? It can be at most L steps before, I mean, its correct position can be at most L steps to the left. Okay, because uh, yeah, because if not, then this element here would also have had an inversion with the I plus 1th element. Okay, so that is the observation which you are implicitly using. Does that make sense, or do you want me to repeat? Okay, so observe that if a of I plus 1 has L inversions, then the correct position of ai plus 1 in the sorted array is at most L steps to the left. Okay, and okay, yeah, and observe that when we do this, when we keep sorting this array, okay, you're not introducing any more inversions. The number of inversions can only go down because the elements are kind of falling into the correct place. So the number of violations you had earlier can only go down, it can never increase. So the worst case that could happen is that you end up spending order and amount of time in the outer loop of insertion sort, and you would end up using at most order k or exactly k uh, k many comparisons in finding the correct position. Okay, so altogether you are incurring a cost in the worst case of order n plus k, which is the yeah. So I think yeah, that is consistent with what you had in mind. So, but if there are any questions, let me know. Okay, so I'm looking at one comment right now, which says that any comparison based sort takes n log n, um, at least n log n. That is correct, but the statement is correct when you have an arbitrary array. So if you have no additional information about the array, then it must take in the you can come up with an input where it will take n log n comparisons. But this is not a general case because you have this additional information, right? Um, so what could be k in the worst case? What can you come up with a bad, like a rough bound for it? Mm, okay, yeah. So worst case would be roughly order n square because um, I mean the I comma j pairs are n choose 2, and let's say your array is reverse sorted, it's entirely reverse sorted. So every pair of elements will cause a violation. So you will have roughly n choose 2 um, many inversions in the worst case. So if you put that in this bound, then you're doing n plus n choose 2, which is roughly n square. So you're still doing bad. So in general, it won't work better, but given that k is small, k is a constant, then you are doing linear. Yeah, what I mean is array is reverse sorted in the sense all the elements are in the descending order. Okay. Um, any other questions related to this? Is I hope this was clear. Mm, okay. So okay, there is one comment here, which says okay. So, if you have questions related to the videos that were uploaded, okay, the lecture videos, then there's a discussion forum. You can put it up there, and there are TAs who are designated to, I mean, who will look into it. Um, in the problem solving sessions, what we'll generally do is um, we will come up, I mean, I'll generally have a set of questions prepared and we will discuss those. But if you have more questions, then you can maybe dictate it to me and we can take it up. But if you have like doubts that are specific to the lectures, then use the discussion forum, which is on on this YM portal itself. When you log into the course, you should find a tab called discussion or Q&A, something like that. So okay. Okay, so we will be taking up questions of similar kind, the binary exponential, the squared, repeated squaring, um, in some time. So if it naturally comes up, then you can let me know. We can discuss it. Okay. Okay. Um. Okay. So this is a slightly simpler question, but for the sake of exercise, just try it out. So you have an array of 4 elements. Um, so what is the in the worst case, what is the maximum number of comparisons you would end up doing? Like, come up with a worst case input.
Eight mark?
Can you do better? Um, okay. Um, yeah, so a lot of answers on the chat say 5, so that is okay. Mm, okay, so I think 5 is the correct answer, but yeah, so one of you who thinks it's 5, can you explain the reasoning?
Because in the first case, it will become 1 plus 1 is equal to 2. In the second level, while merging two sorted arrays, size 2 into size 4, it becomes 2 plus 2 minus 1, which means 3. 2 plus 3 is equal to 5.
Correct, yeah, good. So in the first step, you will split the array into half. So you are going to compare this and this, and there you are spending one comparison and a one comparison here. So in the first step, you have um, com- made two comparisons. Now you need to merge these arrays. So let's say this is 2 and 6, and let's say this is 3 and 5. So uh, if you have an array of size n here and an array of size m here, and let's say these are sorted, both of these are sorted, and you want to merge them into a sorted array, the number of comparisons you need to make would be n plus m minus 1. So which is, in this case, which is 3. So altogether you would end up spending you end up making 5 comparisons. And yeah, indeed, in this example you need to make um, 5 comparisons. You can't do better. So yeah, maybe verify it in your own time. But yeah, uh, yeah, I'll not get into the details. So, but is this okay? Or if those of you who had larger answers, is this okay? Okay. Okay. So I'll just okay. Let's just look at this example and see what happens. Okay, so I hope you agree that here you needed one comparison to sort this smaller array, and you needed one comparison to sort this array. It could have been in any order, right? So you have spent two comparisons already. Now your task is to merge these two. Okay, so how does the algorithm proceed? You look at uh, yeah, you look at the first element here and the first element here, and you compare which of these is smaller. In this case 2 is smaller, so you write 2 and update your pointer to the next element. And now you compare 6 and 3. You see that so you've already spent one comparison here. This is the second comparison you're making. You're comparing 6 and 3, so the smaller one is 3. You write it here and update this pointer to the next one. Now you're comparing 6 and 5, and you write 5. The remaining element uh, is 6, right? So how many comparisons did you make? You made 1 plus 1 plus 1, which is 3 comparisons, which gives you 5. And in general, to see this n plus m minus 1, uh, the idea is that you are okay, so you have this imagine that this is your n plus m sized array. So let's say these are n elements, these are m elements, and these two are sorted amongst themselves. So what you was kind of doing is you are linearly going at every point, you are moving one of the pointers, right? So when you compared 2 and 3 and you got your answer, you moved this pointer to the next step. When you compared 6 and 3 and got your answer as 3, you moved this pointer to the next step. So every time you make a comparison, you are making progress by 1, right? So if there are n plus 1 elements, n plus m elements, to get all the way to the end, you're doing all like every time you're making a progress by 1, but only in the last element. For the last element you don't need to do any comparison, because the remaining element will fill up this space. So that's what this minus 1 is about, and that's the intuition. um okay, okay, good. uh okay. Okay, I'll just a minute. Okay, so this is okay, so this part of the question has nothing to do with algorithm design. This is just an analysis. um, so let's say you have um, yeah, okay, you want to come up with a hmm, okay, just a second. hmm. Okay, so if you do a very brute analysis, you can say that okay, all of these elements, uh, this element is at most um, hmm, okay, hmm, okay, okay. If you assume that every element, there are n elements that you have, and assume that all of them have a value of at most n, then you get n square. But okay, but yeah, if you do a slightly better analysis, uh, observe that log of n factorial is nothing but log of okay, so this is product of n minus 1 all the way up to 1, And now if you use the identity, what you will have is this is log n plus log of n minus 1 plus log 2 plus log 1 and so on. Okay, so so this is essentially the sum that you wanted. And okay, so if you want to bound this, you can as well bound n factorial. So if you use the yeah, if you use the Stirling's approximation, you'll find that n factorial is at most 2 to the n log n. There must be some constant here. So log of which is order n log n. So as most of you answered. Okay. Yeah, so yeah, that the brute approximation also works. You can do, if you do, even if you do without the Stirling's approximation and approximate it with n to the n, you would still end up getting n log n. Is there any other question? I think I saw a raised hand at some point. Okay. 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 So okay. So yeah, this is this is a hypothesis which may or may not be correct. If it is correct, you have to come up with an analysis. If it's not, then come up with a reasoning why this is wrong. Okay, so what is the idea? Your insertion sort yeah, so your insertion sort essentially maintains some sorted part, and then you're going to put this ith element in its correct position. So as you all said earlier, this takes order I amount of time now, and therefore the total number of time ends up getting yeah, n squared in. Okay, you'll do order n, you'll do n plus n minus 1 plus all the way up to 1, and this turns out to be order n square. That was your analysis. So here is a thought. Okay. Okay, so here is a proposed algorithm. So instead of going all the way back to I, what if I use I know that this array is already sorted. Okay, so it's not arbitrary, it's already sorted. So you can do a binary search algorithm. Okay, so this would take, if you instead of linearly finding the correct position of I of the ith element, what you do is use the binary search algorithm. Okay, so how much time does this take? Your array is of size I roughly, so this should take log I amount of time. Okay, so if you do this, then the first element takes log 1 amount of time, the second element takes log 2, and you keep on summing this. The last element should take log n amount of time, and the sum of this, as we saw, the sum of this, as we saw in the previous question, turns out to be n log n. So this seems to be giving you some improvement, but is this correct? Is this indeed a faster algorithm, or is there something fishy that you see. Someone had raised a hand. If you have a question, you can ask. Yeah. I hope the question is clear. Let me know if any part of this should be repeated. Is the question clear? Um, um, any thoughts is, I mean, it may not be correct. If you have any thoughts that come up, you can feel free to share. Mm, okay. N square, as in, are you saying that the analysis is the problem, or the idea of using binary search is the issue? Yeah, yeah, Hriday, I think, yeah, that's correct. So it's not enough to find the position, the correct position of the ith element. You have to actually uh, swap it with the element here and then push all the other elements. So pushing those elements will take order at time in the worst case. So just finding is not an issue. Good. So this doesn't work. So yeah, the issue is that all because finding the correct position is not enough. Okay, so this is an issue because the data structure that you're dealing with is is an array. So let's say that this were a linked list, okay, where uh, let's say I have a sorted linked list, and now I know that okay, this is the correct position for a new element. So what I'll do is I will update this pointer as such, remove this, and get a sorted I mean a sorted linked list. So does this mean that if I were to use linked list instead of array, then I'm doing something better in terms of time? Okay, so I'll just repeat the gist of this discussion. So, okay, so one thing is that this course assumes um, some basic, I mean, some exposure to data structures, and some notations, this order and so on, some part of uh, um, the definitions from the design and analysis of algorithms course. So it may not be possible to I mean, we can uh, roughly, I mean, quickly introduce the notion, but it may not be possible to cover in depth understanding and introduction of these notions. So okay, so okay, so let me just repeat uh, this question. Okay, so you had an array and you were to perform insertion sort. You are going to put the ith element in its correct position. So we said, instead of linearly going for it, why don't you use binary search? Binary search takes logarithmic amount of time for searching. Okay, so so that was the idea. For ith element, you would end up using log I number of comparisons. So you added up all the terms. Okay, this is the time for the sorting the entire sort, and this sum turns out to be n log n, as you saw earlier. But the problem, as some of you pointed out, is that uh, this may not work, because you don't just have to find the correct position, you actually have to place it there and then make sure that the entire array up to I elements is sorted. But array will have, I mean, because the data structure you're using is array, you'll have to uh, do it like one at a time. Okay, so in the worst case, you will need order I amount of time per element. So the analysis gives you order n square. Okay, but the question is, instead of array, if I use linked list, I can do this insertion quickly, right? If I know the correct position, I just need to update 2 pointers. So this is order one amount of time. So does this mean that instead of array, if I were to use linked list, I can do better? Is the question clear now? Okay, so does anybody agree that if I were to use linked list, I can do n log n, or something asymptotically better than n square? Mm, yeah, so yeah, you're right. So you can't do better, but what is the reason? Um, are there any thoughts?
Yes, ma'am. For the first insertion, I think I'll take O of one time. Similarly, for the second insertion, O of two, and n insertions may be O of n. And if we add 1 plus 2 plus 3, it's n square plus n by 2, and worst case is n square. So we still back to
Hmm.
square one.
Yeah, you can't. Yeah, so inserting is as such not a problem. Inserting will take you order one amount of time, but you can't use your classical binary search algorithm for the linked list. So you can't do this order log n thing in linked list. So you will, yeah, you'll end up using uh, order n square time in the worst case. So in case of arrays, uh, the searching was not an issue. The searching saved you some time, but making the insertion was the factor where you ended up spending more time. If you use linked list, then insertion is not an issue. Insertion is an order one operation, but the searching is an issue. So can you come up with a data structure which uses this fast searching, the binary searching idea of arrays, but the quick insertion of linked list? So there is something called tree sort. I'll not okay, I'll just write the conclusion. So if you use array, then searching is order log n, but inserting, let me say order log I, but inserting will take order I time. And if you use linked list, then insertion is order 1, but searching is order I. Okay, so there's a data structure which uses the good parts of both of these, which is called I think it's called tree sort. I'm not entirely sure. Okay, I need to confirm this. So this this will make sure that you can um, do a search as well as insert both of them in order log I. So altogether you would you would end up doing the entire sorting in n log n. So if you are interested, you can look it up, but yeah, we will not get into the details of it. But I hope the point is clear, like why this strategy does not work. I hope that is clear. Okay. Any questions? Okay, good. So yeah, I think yeah, so I wanted to address this comment as well. So yeah, Sagnik, yeah, thank you for the pointing out the resources. um, yeah, those of you who would like to refresh the basic concepts, this course by Professor Saurav Mukhopadhyay is a good place to catch up, um, with the fundamentals of um the I mean concepts that we will use in this course. Yeah, the other course I have not checked out, but yeah, feel free to look into it. Okay, yeah, thanks for pointing out. Okay. Okay. um, okay. Okay, so let's recall your subset sum question. So input to you is an array A of size n. Okay, and you are given an integer k. You're going to say yes if there is uh, a subset B of A such that if you sum up mm, the entries in the set B, then you get integer k. Okay, otherwise you will say no. So this is yeah. Yeah, so this is a problem that you must have seen earlier. So what is a brute force strategy for doing this? Like very rough estimate. Okay, so what are the two for loops? You'll search for um, oh, the subset need not be contiguous, by the way. The subset can be arbitrary element. So you can take the second element, the fifth element, and then the 10th element. It need not be a contiguous set. Is the problem and the question clear? So um, yeah, yeah, Aditya, that's correct. So you're going to try all combinations, that is, go through all subsets and find their sum and check if it is equal to k. So okay, so how many subsets are there? So the idea one is that go through all subsets and check if the sum of elements in B is equal to k. So the second step is takes linear time. Let's say there are order n elements in the set B. Summing up is a, let's say, let's say it takes order one time. So overall you are spending order and time in finding the sum and checking if it is equal to k. So but how many times do you need to do this? So what is this bound? Okay. Okay, so if you go through a brute force idea, then this is 2 power n, because for every element you are deciding whether to choose that element or not. So so for every element you have a choice, you have two choices, whether to take it or not. So this gives you 2 to the n possible subsets. Okay, now you can say that okay, I'll do something slightly better. I don't need to go through all the subsets. Let's say okay, um, let's say B is a subset that I'm looking at, and the sum of elements in it is L. So do I need to check for um, okay, so I can just check whether this sum is equal to k, or what I can do is I can check if this sum is equal to the sum of um, all the elements in A minus uh, minus k. Okay, so what does this mean? If B or the complement set of B has a sum of k, then I will catch it in this step itself. Okay, so by doing this I'm removing one set. For every set we are saying that its complement is redundant. Okay, is this fine? So by doing this, what will happen is you have reduced the number of the total number of sets by half, because you don't need the complement of a set. You are just going to check it in the sum, check it in this step itself. So you're reducing the total number of sets by half. So this is 2 to the n minus 1, which is slightly better, not much better. It's still exponential. So but I hope this idea was clear. So we are removing complements from the operation. Okay, from the loop. Okay, so but this is not I mean as good as we wanted. It's a slight improvement. So can we do something better? um, yeah, those of you who have, yeah, Akshit, uh, is it clear what we are trying to do? I mean, the general flavor and question. If you want me to repeat some part of it, let me know. Yeah, so yeah, you're right. So this you have 2 to the n subsets, and uh, yeah, so this was the first brute force algorithm. You go through all possible subsets, right? So there are 2 to the n possible subsets, checking sum, finding the sum and checking whether it is equal to k. That takes n times. So altogether this would have taken us n times 2 to the n time. Okay, the question is, can I do slightly better? So the for so the idea was that, um, let's say that the sum of your entire array A is equal to S. Okay, so if you sum up all the elements, okay, um, okay, this sum is S. Okay, if and let's say I'm looking at some subset B. Okay, and we are actually checking whether the sum of elements here is equal to k. Okay, so if this sum is equal to k, what is the sum of the complementary set of this? So let's say B complement is this set, sorry, A minus B, then what is this sum going to be? Yeah, good. So this is S minus k. So what we're saying is, in this loop that we were going through, you are looking through all possible subsets. Instead, let me do one thing. If I'm looking at a set B, I will not uh, iterate over this set B complement. Instead, what I'll do is, in this step itself, check if the summation of bi is equal to k or S minus k, because even if summation of bi is S minus k, that means the complementary set, uh, I mean, if you sum up the elements in the complementary set, you will get a sum of k, and you will end up saying yes. So instead of iterating over this, I will make that check here itself. So by doing this, we are saying that half the sets are redundant. You don't need to spend order and amount of time here in finding the sum, because you already know that the sum is going to be S minus k. Yeah, S minus k may be equal to k. That is not a problem, because you will anyway, the answer will be yes. Okay, so that was the idea, that half the sets are redundant. So therefore, out of the 2 to the n possible, all possible sets, only half of them are the ones through which we are going. So this is 2 to the n minus 1. Okay, what is the question? So if the summation of pi is equal to, yeah, you are right. So if the summation of elements in bi is equal to S minus k, that means the remaining subset, the complementary subset, gives you a sum of k. But remember that this is a decision problem, right? So you only need to tell yes or no, whether there is a subset whose sum is k or not. That's all. You don't need to give the subset. Okay, good. So that's it. So you have reduced the total number of sets to 2 to the n minus 1, and therefore the total amount of time will be n times 2 to the n minus 1. So that was one idea of reducing, the time by, um, yeah, by counting fewer number of sets. Okay, but can you do something even better? Let's say I don't want this to be 2 to the n minus 1, I want this to be 2 to the n by 2, so that the total running time becomes. So can you think of something cleverer? Okay, so let me give a hint. Okay, so we will in some sense use this idea, but okay, let's start with the following thought. Let's say that I divide my entire set into two parts. So this is the first n by 2 elements, and these are the remaining n by 2 elements. Okay, so assume that n was even, but it doesn't matter. Okay, so now what you do is you go through all the subsets of, I'll call this A1 and this is A2, the first half of the array and the second half of the array. So you go through all possible subsets of A1. So how many subsets are there? Um, okay, so how many subsets of A1 are there? Yeah, good. So this is 2 to the n by 2 many subsets, and similarly you go through all possible subsets of A2. Do the same thing for A2. So there are 2 to the n by 2 subsets. So now can you and then find out the sum of all the subsets. So this step 2 is the same. Go through the subsets, go through all possible subsets and find their sums. So let's say uh, for each of them you're going to find the sum. So this will take you roughly n by 2 amount of time. This factor is because you are summing the entries, and same thing happens here. This factor is because of the sum, right? So now you have uh, you have the sums of all possible subsets of A1 and the sums of all possible subsets of A2 that are available to you. So what can you do to check if the original set A has a subset whose sum is equal to K? Okay, so let's do the next step as well. So this is where we were, and you are suggesting that okay, let's sort these sums. So how much time does this take? We are going to sort 2 to the n by 2 sums. So how much time does this take? You have an array of size 2 to the n by 2. Use your favorite sorting algorithm. How much time will this take? Um, yeah, so you have 2 to the n by 2 elements with you and you're going to sort. So how much time does it take? If you have n elements, if you use merge sort or something, you take n log n time. So substitute n with 2 to the n by 2, you get log of 2 to the n by 2, which is n by 2 times 2 to the n by 2. So this is the amount of time you ended up spending in sorting. Is this fine with everyone until this point? Okay, so you do the same thing here as well. You have this set A2, go through all possible subsets. There are 2 to the n by 2 subsets. Find the sum of every subset that takes n by 2 time. And now you're going to sort again. So again you have 2 to the n by 2 elements and you're going to sort it, and this will separately take n by 2 times 2 to the n by 2 time. for the sorting. Okay, so we did sorting, that incurred us some time. Okay, so now what can you do with this? You have you have these you have this information available to you. What can you do to check whether there's a subset in the original set whose sum is equal to k? Okay, so let's ask one more question. So you have this array A, and let's say there is some subset here whose sum is equal to k1. Okay, so um, so uh, what should be the value of some subset here in A2, so that the original, um, let me call this S1, let me call this S2. So what should be the value of uh, the summation of a subset in A2, so that k1 plus summation of S2 of I gives you the actual sum that you wanted, which is k. Okay, so then you will say that S1 union S2 uh, is a subset of A whose sum is equal to, okay, so by this I mean the element sum. Okay, so is this fine? Okay, so okay, so in other words, what is the subset sum, the value of uh, the sum of a subset here that you're looking for? This should be k minus k1. That's what you're looking for, right? So this should be equal to k minus k1. So if the value of a subset S1 in A1 is k1, then you're looking for a subset inside A2 whose value is k minus k1. If that is found, then you have a bigger set whose sum is equal to k. Um, is this okay? So if this is clear, can someone fill up the rest of the thoughts? So what will you do? How will you efficiently find, given that you have a sorted array here and a sorted array here, how will you efficiently find whether there is a uh, subset S with some k? Even a naive strategy is fine to start with. If there are any questions or doubts, please let me know. Okay, so let us simplify the question. Uh, let us say you have this is the sums of subsets. So you had 2 to the n by 2 subsets, and this set stores the sums. Okay, so for subset 1, subset 2, and so on up to subset 2 to the n by 2. And similarly, you have the set of sums for the other half. Okay. Mm. Okay, so, and let's assume now it's not even sorted. Okay, you've just looked at the subsets and you've put the sum here. So what is your natural strategy? You'll take a subset here, check if the sum is equal to k, right? So what would be your assume that the arrays are not sorted. Then what you will do is, um, let me call this a1, let me call this entire array a2. For each subset sum in a1 and for each subset sum in a2. So suppose this is l1, this is l2. Check if l1 plus l2 is equal to k. If yes, then halt. Okay, and at the end of this loop, if nothing is found, then say no. Okay, so that's the brute force idea, right? So how much time does this take? Anybody? Goyal? Okay, so how much time does this take? How many arrays are there? How many elements are there in this for loop? There are 2 to the n by 2 elements here. So there are 2 to the n by 2 elements here. There are 2 to the n by 2 elements here. So you are running these independently. So altogether this is 2 to the n by 2 times 2 to the n by 2, and you're spending, um, let's say this is an order 1 operation. Okay, so what is this total time? This is 2 to the n. Okay, so you're not really doing much of a saving here, right? If there are any questions at this point, please let me know. Otherwise, does everyone agree that like this is the amount of time you will end up spending if you do a brute force uh, algorithm for checking the sum? I'm audible, right? Okay, so if let's say these arrays were sorted, let's say that a1 is given to me as sorted array and a2 is given to me as a sorted array, do I really need to go through all these pairs, check for each of these pairs and see whether the sum is equal to k? Because now there is more structure in the array, so can I use the sortedness to save some time? Okay, so let me describe one algorithm. If you have other ideas or any questions after that, then let me know. So suppose that sum of subsets is sorted now. So a1 is the sum of subsets of let's say this is subset 1, subset 2 to the n by 2, and this is sorted. Okay, so this is a sorted array. Similarly for a2 also we have performed the sorting, and this is also sorted. Okay, so now let me look at this value. Okay, so let us say that this value is a1. Okay, um, and then let me look at this value. Okay, let me look at this value, and let's say this is b2 to the n by 2. So this is a1 a2 up to a2 to the n by 2, and this is, let's say, b1 b2 up to b2 to the n by 2, where a1 is less than equal to a2, and so on. Similarly for b. Okay, so let me look at these two values and check whether the sum is equal to k. So check if a1 plus b2 to the n by 2 is equal to k. If yes, that means the first that means the subset corresponding to the first element here and the subset corresponding to the last element here is the union of these two subsets gives you a sum of k. Correct? So if this is the case, then you're going to stop the algorithm and say yes, there is a subset which achieves the sum. Otherwise, what can happen is a1 plus b2 to the n by 2 is less than k, or what could happen is a1 plus b2 to the n by 2 is greater than k. Okay, so in this case, let's say that the sum of this and the sum of this is actually smaller than the value that you were looking for. Then what does this say about your next search? So you can borrow some intuition from merge sort that we did earlier. um, the fact that these two arrays are sorted tells you something, if the sum is less than k. Okay, so if if a1 plus b plus this element, if this sum is less than k, is it possible that a1 plus b j, by j I mean j is in some element here. Okay, is it possible that some bj achieves this? Is the question clear? Is the question making sense? Maybe I'll repeat it one more time. So you're looking at this element a1 and this element b 2 to the n by 2, and the sum of these two is less than k. And note that these arrays are sorted. Both the arrays are sorted. So if this sum is less than k, is it possible that by replacing b n to the 2 by b2 to the n by 2 with some other element here, okay, is it possible that I get a sum equal to k? Okay, good. Exactly. So you can't do that because any element any element before this is smaller. So if this sum itself is smaller, then that sum cannot be larger. So this is not possible. Good. So then that means, what does this mean? You should not look at a1. A1 is the wrong element to look at. You should actually be looking at a2 because a2 is larger. So the hope is that a2 plus some other element here maybe gives you uh, the value k that you're looking for. So then what you will do is you will update your counter to a2. So initially I was pointing at 1 in the array a1 and j was pointing at 2 to the n by 2 in a2. But if a1 plus b2 to the n by 2 is less than k, then what you should do is you should increment I. Then I is equal to I plus 1. That's what you should do and continue the search. Okay, now let's look at the other case. Let's say that a1 plus this sum is larger than k, it's larger than the value you're looking for. Then what does this say about, can you do a similar analysis here and increment or decrement one of the pointers? Yeah, good, exactly. So uh, that is indeed correct. So what you're saying is if a1 plus b, um, 2 to the n by 2 is greater than k, then for all ai, or let's say aj plus b to the n by 2, this sum is going to be greater than k. So if you fix your last element to be this this b 2 to the n by 2, then no matter what a you take here, you will always get a sum which is larger than k because all the elements here are larger. So you're only increasing this total summation if you take anything other than a1. So that means this is not the correct element to look at. This is not the correct element, so you decrement your counter by 1. So in this case, um, if a1 plus b 2 to the n by 2 is greater than k, then you're going to decrement the value of j counter. So initially I was here and j was here. If you are in this case, you're going to increment a, and if you're in this case, you're going to decrement k, and then you continue this until you have your I pointer is here and j pointer is here, and that's your final entry. So how much time does this take? Yeah, good. So what you are doing is, so in every step you are either you're either shifting your I by one step or you are shifting your j by one step. So you are going to meet somewhere in the middle, unless you have already found your answer. So this is 2 to the n by 2, the size of the array, plus 2 to the n by 2. So this is 2 to the n by 2 plus 1. Does that make sense? Your the size of your array was n 2 to the n by 2, right? So total time for finding sum in the sorted array. So this is the total time for finding the sum. Okay, so what is the total amount of time that we spent? Initially, we went through all possible n by 2 sized subsets. So this was I okay. I'm audible, right? Okay, so let's do the total time analysis. So what you did was you divided your set. Yeah, thank you. So you divided your array into two arrays, A1 and A2, and then you went through all possible subsets. So this was a brute force thing. So that was 2 to the n by 2 and 2 to the n by 2 for the other array. And then you went on to find the sum. So that the cost you incurred there was uh, n by 2 times 2 to the n by 2 plus n by 2 times 2 to the n by 2, which is n times 2 to the n by 2. And then you sorted this individually. So okay, yeah, and then you sorted this individually, which was again order uh, yeah, which is again order n times 2 to the n by 2. And final step was this merging idea, which borrows intuition from merge sort. You have two sorted arrays. You want to check whether there is an element here and there is an element here, the sum of which is equal to k. So you went through this procedure step by step. You started your counter here and the j counter here, and at every step you are either moving the ith counter or the jth counter. So altogether this was 2 to the n by 2 plus, so I'll call this the sum check routine. Okay, so this sum check took you um, 2 times 2 to the n by 2 amount of time. And yeah, if you add all these times together, the dominant term here is n times 2 to the n by 2. So overall your algorithm runs in this amount of time. So yeah, does this make sense, or is there any part in this algorithm, I mean, where you would want some clarification? So was this clear? Is this clear to everyone? Okay, so okay, so okay, I'll not take up the next question for today, but yeah, will yeah, I plan to take it in the next tutorial, which will hopefully clarify. Some of you had some questions about the repeated squaring, so hopefully um, yeah, hopefully it will come up. So it will take some time to go through the question, so I'll not take it now because we are almost out of time. So if there are any questions about anything we discussed today, any of the questions, then let me know. Otherwise, we will meet next week at the same time. So Tuesday, which is Tuesday 7 p.m. to 9 p.m. But if there are any questions, then let me know. Yes, that was, yeah, Goel, that was the question, but we'll take it up next time. Mm. Okay, yeah, sure, that I can do. So let me, maybe I'll not do the analysis, but we will just go through the basic idea. Okay, so the idea is that your Fibonacci number, the nth Fibonacci number is defined as follows. Okay, so let's say, yeah, I mean, let me start with one. Okay, let's say these are your two numbers. The next term is going to be the sum of the previous two, so this will be 2. The next term is going to be the sum of the previous two, and so 5 and 8 and so on. Okay, that's your yeah, that's your Fibonacci sequence, or also called as Hemachandra numbers. By the way, if you look into the history of this, uh, so this dates back to ancient Indian history, where Hemachandra was apparently the first person to discover this sequence. So it's also called Hemachandra numbers, by the way. So this is your sequence, and the idea is as follows. You are given a number n, and you want to output the nth Fibonacci number. Okay, so what is the strategy? You in order to find, let's say, f of 5, you need to find f of 4, f of 3, and sum them up. But in order to find f of 4, you need to find f of 3, f of 2, and yeah, so it's, if you expand the recursion, it's going to be a tree. So okay, so there is a lot of computation that's wasted here, right? I mean, you are redundantly calculating the same thing again and again. So for example, f of 2 is being computed at these two places, then f of 3 is being computed here, and if this n was large, then there is a lot of computation that's going wasted. So okay, so that is one issue. The other issue is that, which is not so big, the other issue is that this number could be very large, right? So f of, even though these are small numbers, the nth Fibonacci number could potentially be exponential in terms of n. It's roughly 1.5 to the n or something. So that is another issue. Even though n is small, the value itself could be larger, but that's not a major issue for us. Okay, so the idea is that this method of using this sequence is wasteful, in the sense that you are only finding the third term, then you're finding the fourth term, then fifth term, and you're linearly doing this. So in order to find the nth term, you are finding all the terms before it. So that is the wasteful computation. So right, so what you could do is, if I want to find, let's say, assume that n is a power of 2, I want to find the nth Fibonacci number. Okay, so what if I could use what if I could instead of going to f of n minus 1, instead of doing that, let me jump all the way down and find f of n by 2. Okay. Yeah, sorry, I was not looking at the questions. Yeah, I'm assuming an arbitrary value. Let us, it just becomes easier if n is a power of 2, but if it is not, then you can do something. You need to do some extra steps to make it work for. Okay. So, okay. So, so let's say that I don't want to do this linearly. Okay. Then, if I can make you jump all the way down to f of n by 2, and you ask the same thing here, in order to find f of n by 2, what if I could, skip all these elements in between and just find f of n by 4, and so on. So you are logarithmically reducing the number of steps. That's the idea, that instead of going to the next one, or let's say the previous one, you are skipping all the way back, hoping that you are saving time at the end, like altogether. So why does this, like, so how do you do this? You observe that if let's say I look at this matrix, okay, let's say this is f of n and this is f of n minus 1. Okay. Okay, so this is a matrix. I'm calling this matrix A. Okay. Multiply this matrix A with this vector f of n minus 1 and f of n minus 2. This turns out to be f of n minus 1 plus f of n minus 2. This is the first entry, this row and this column. And if you look at the second entry, this is going to be simply f of n minus 1. Okay, but what is f of n minus 1 plus f of n minus 2? It is f of n, correct? Is this fine with everyone? So if I look at this matrix and multiply with this vector, I'm going to get back this. Okay, now you do the same thing again, because okay, so let me get this on the new page as well. Okay, so yeah, I call this matrix A. Now let me do the same thing again. Okay, what I can do is I can say f of n minus 1, f of n minus 2 is nothing but 1 1 1 0, f of n minus 3, f of n minus 4, right? You're just replacing the variable n with this. So what does this give me? By replacing this with this term, this gives you 1 1 1 0, 1 1 1 0, and f of n minus 3, f of n minus 4, which is nothing but a square times f of n minus 3, f of n minus 4. Now if you keep on repeating this, okay, a to the, I think this should be n minus okay, okay, I'll calculate this, back calculate this, but this is going to be f of 2 and this is going to be f of 1. Okay, so what you're doing is continuously keep replacing this with yeah, with this formula, and every time you are multiplying with an a and reducing this n minus 3 to n minus 4, n minus 5, and so on. Okay, does this make sense? Okay. Okay, so this may be n minus 3 or something. We just I mean, you can find it out later, but yeah, I think this should be n minus 3. Yeah, so the point is, I already know the value of f of 2 and I know the value of f of 1. This is let's say 1 1. Okay, I don't need to do anything here. The only thing I need to compute is this, a to the n minus 3. Okay, just find it out later. Let me just assume that this is a to the n minus 3. Right, so point is I want to efficiently calculate this. One way to do this would be linear thing. You do a into a and so on n minus 3 times. That is one way of doing it. But you can do something better. So what is that? Or let me take a simpler question that you might have already seen. Let's say you want to find the product of this, and let's say these are 64 terms. Okay, so you want to calculate the value of this by multiplication. Don't use any other means. So how would you efficiently do this? Yeah, squaring and adding. So what I'll do is divide this into half. So look at these 32 terms, find this product. Let's say this product is p. The other half I don't need to calculate, right? That's going to be the same. So I just need to find this p and square it. That's all. So, and then you can say the same thing. In order to find the product of these 32 terms, why don't I think of it as 16 terms and 16 terms? Find this and then square it. So you'll find the product of 2 terms, use it to find the product of 4 terms, use it to find product of 16 terms, 32 and 64. So the number of products you ended up doing is not 64, which it would have been if you did the brute force thing, but is logarithmic, log of 64, which is like 5 or something. Yeah, log n minus 1. So you can do the same, apply the same logic here. If these are, let's say, 2 to the k terms, I'm assuming it's a power of 2, then you are going to find 8 times 8. Okay. In order to find a2 to the k, this is nothing but a2 to the k minus 1 times a2 to the k minus 1. Sorry, yeah. And then this is going to be a2 to the k minus 2, a2 to the k minus 2, and so on. Yeah, you keep on doing this, right? So how many multiplications you would end up doing? This will be logarithmic, log of 2 to the k, so which is k multiplications. Okay, so that is this idea is called repeated squaring. Okay, uh, okay, so yeah, if you can look into the analysis of this in the lectures, but yeah, that was that is the overall idea. Okay, so yeah, I hope this session was useful. If so, this is how we will proceed in the remaining tutorials as well. We'll look at the questions relevant to the contents covered in that week, and if you have questions that related to the content, you can raise it during the tutorials. Okay. Okay, thank you also. Yeah, why? So this will be uploaded on YouTube. You can check it out from the link in this one. Okay. Okay. So, okay. Bye all.